Okay, good morning. Let's begin with questions. Does anybody have any questions they want to get answered about transient analysis, AC analysis, any of the homework, any concepts? Okay. All right. Let's go to the notebook then. Lecture 19. Okay, so let me clarify a few more concepts. So we're discussing AC analysis using sinusoidal waveforms, right? So the reason we describe this AC analysis separately is because of capacitors and inductors. Okay, for a resistor, the response from a resistor is the same for AC as well as DC input. Okay, so if you apply a DC voltage or DC current to a resistor, you'd obtain some response. If you apply an AC voltage or AC current to a resistor, you would elicit this exact same response, meaning electrical energy is being transferred to the resistor and it dissipates it in the form of heat, thermal energy. However, when it comes to capacitors and inductors, well, it's a little bit different. Well, it's a lot different. It's because capacitors and inductors are energy storage devices. We saw in chapters 3 and 4 that energy can be transferred into these devices, into these components, which they can store for a period of time and then later release it back into the circuit. So if we apply DC, if you apply DC voltage, what does it mean? We're applying a DC energy source to a capacitor or inductor. They will receive the energy, they will absorb it, they will store it, and they will release it back into the circuit when the input is removed or when circumstances change. Now, instead of DC, if you apply AC, what happens? Well, with AC, it alternates between a positive and a negative peak. So, capacitor and inductor will receive energy, and because the input voltage or input current is alternating between a positive and negative, it will flow out in the next half cycle. So if we divide the AC voltage or AC voltage or current, the waveform into two half cycles, one positive, one negative. In one half cycle, the energy will flow into the device or into the component. In the other half cycle, the energy will flow out. And this happens constantly. Okay, so the behavior for a inductor or a capacitor is completely different when it comes to AC. Okay, The relationship for a capacitor and inductor is the time rate derivative or the integral, right? So for a capacitor, capacitor voltage V of t, capacitor current I of t is given by C dV over dt. The capacitor current is the time rate derivative of the voltage, and capacitor voltage is the integral of the current. For an inductor, the inductor voltage is the time rate derivative of the inductor current, L di over dt. So now, if we try to solve these for an AC input, we are required to solve differential equations. I don't know about you, but that's not my idea of a fun time. Not unless you really like math and you want to solve differential integrals, differential equations for fun, right? So in order to not do complex math like that, what we do is we perform some conversions, okay? And we use complex math, meaning complex number math, to make our math less complex. Okay, so that's what we're doing in AC analysis in chapter 5. So chapter 5, 6, and 5.5, or chapter 7, if you will, AC analysis, AC power, and filters, they all require the usage of complex number math, imaginary number. Okay. So we looked at fundamental concepts of an AC waveform. We talked about magnitude, amplitude, or peak values. Talked about the frequency. We talked about the phase. Okay. Does anyone have any questions about these three quantities? Okay. All right. So now let's talk about the values of these different quantities. So sine waves, or any kind of waveform that is symmetrical around the x-axis, meaning it has half its value above x-axis and half its value below, what would be the average value for this waveform? If it's exactly half above and half below, it will be 0, right? Average value would be 0. Yet, when we apply an AC voltage to a circuit, energy is still being transferred. So mathematically, if the average value is 0, how can we represent the energy that is being transferred? How can we represent the response that is generated in the circuit? Well, then scientists and engineers figured out a way. Said instead of taking the average value of the waveform, what we'll do is we'll first take square of the waveform. So if this is our voltage or current, for that matter, we will square it. And then we will take the average of the square. Okay, then we will take the average of the square. And so take the average, you integrate over one time period and divide by the number of cycles, meaning the time period. And because we took the square at the beginning of our calculation, at the end, we will now take the square root. So they came up with a quantity to describe, so we came up with a quantity to describe the average value of the waveform. And that came to be known as the root mean square. It literally is the square root of the mean of the square of the waveform. Okay. And the acronym for this is RMS. And the RMS value of the waveform is the corresponding value of an AC voltage that would generate the same response in a resistor as the equivalent DC value. So think of it as the same exact DC value of an AC waveform. Okay. If we take this waveform And let's say we convert it into 2 positive peaks. And now at any given point in time, the value of this waveform changes. So think of this as a couple of mountains, and we flatten out the dirt completely to make a plateau. That plateau is the RMS value. Okay, that's the RMS value. So it's the same AC voltage, you're just describing it a little differently mathematically. That's all it is. All right, let's take a pause. Let me know if you have any questions. Yes. That's not the same value if you take a single peak and average it. Actually, the answer is yes. I will explain in just a minute. So because this applies to all AC waveforms, it applies to sinusoidal, it applies to triangular, square wave, applies to every single kind of waveform. Okay? It doesn't matter what kind of shape that waveform takes. Okay, but for sinusoidal, meaning for sine waves, and for sine waves only, the RMS value is given by the magnitude divided by √2. So if you were to write VRMS, it would be VM over √2 or VP √2, one single peak. That is simply the mathematical equation that relates it. Okay, that's simply the mathematical equation that relates it. That's all. And what I explained about taking both the peaks in the positive cycle, that's just a tool for explanation. But for sinusoidal only, the direct expression is Vm over √2 or magnitude or peak value over √2, not the peak to peak value. Okay, I want to be clear. Just one peak. Mathematically, we can calculate the RMS value simply by taking one single peak value and dividing by √2. Or we can find the peak value by multiplying by √2. Okay. At this point, I would ask students, our power outlets are AC, right? What is the value of our power voltage of our power outlets? 120. Is that peak or RMS? The clue is, well, one clue I can give is this. RMS is one single number. Okay, it's one single number. If it's a time varying waveform, we say it's V of t, meaning as a function of time, and then we specify the peak value. And then we also specify the mathematical function that explains what that function is. So for sinusoidal waveforms like these, we use the mathematical function sine or cosine. And we say sine x or cos of x. And then we describe the value x of t. So x, the quantity at any given point in time, can be calculated by plugging in the value of time in the equation for sine or cosine. Okay, so the answer is power outlets. Those values are RMS. Okay, if we want the true peak value of our power outlet, you would multiply this by √2. That would give us one peak. If we want it, so this comes out to be approximately 169 volts or something. And if you want a full swing of our power outlets, meaning the maximum possible value, 169 times 2. So 2 peaks, one positive, one negative, approximately equal to 340 volts. That's the total peak voltage, meaning 60 times in 1 second, the power outlet goes to a value of 169 volts. And it also goes to a value of minus 169 volts. And that happens 60 times in 1 second. Okay? Because peak, positive, negative, and 60 hertz sine wave in North America. So 60 times in 1 second, those fluctuations happen. All right. If you measure any quantity using a multimeter, that is always RMS. Okay, so multimeter or any kind of meter will always measure in RMS. If you wish to observe the waveforms, we use an oscilloscope. Okay, so all the lab meters that we have on the lab benches behind us, or if you're taking the lab 251 and you've ever used a multimeter in there to measure voltage or current, that measurement is always in RMS. If you want to calculate the true peak value, then we'd use these equations. Okay. So something like this might come up on the final exam or in any of the quizzes. I might just give a question, power outlet, and then students should be able to understand what is being asked. All right, let's take a pause. Let me know if you have any questions. Anyone? Okay. All right, one final thing before we go to the last slide is the average value of power. We can still use our equations, meaning power is still the product of the voltage and the current. So the instantaneous power at any given point in time can be determined by V of t times I of t. If you remember chapter 1, electrical power is the product of voltage and current. That still holds true. So even for AC analysis, if you wish to find the instantaneous power at any given point in time, then you simply multiply the voltage at that point in time by the current. So P of t is V of t times I of t. However, if you wished to find the average power that is being transferred, then we use the RMS values. And we can still use the equation P is equal to V squared over R, or P is I squared times R. Except in these equations, we now use the RMS values. Again, AC RMS is the DC equivalent of an AC voltage. Okay, that's all it is. Mathematical definition. Right? But the equations still apply. How many of you have done lab 6 in 251? You already completed it? Phasor diagrams? That's interesting. How many of you have lab 6 coming up? Okay. Yeah, 4 minutes left. Lab 6 can get a little. When is your lab 6? Tomorrow. Yours? Wednesday. And you all done the pre-lab? So every lab, I've mentioned this before, every lab has a theoretical section in front. So make sure you read that theoretical section. It also has the equations that you need to solve for the pre-lab. Okay. I have a core lab 6 in the pre-lab videos as well as in the lecture. But lab 6 is all about KVL. Okay, so I'll do I'll leave this for student reading, self-explanatory. But let's go to here. And this is not just about the lab. It'll help you with the concept. So KVL and KCL still apply for AC circuits. Okay. The only thing is, in AC analysis, what we do is, since we convert everything into complex number math, we represent our energy sources, meaning our voltages and our currents are represented as vectors that are rotating in a circle, right? So if we have this kind of AC waveform, we are translating it into a vector rotating counterclockwise. So starting with 0 degrees here and ending with 360. A vector needs only two things, magnitude and direction, meaning all we need is the length of the vector, and we need the angle that it makes with the x-axis. And we can directly describe that AC waveform, right? So if we have a voltage V of t, that is Vp, or let's say Vm cos omega t plus theta, the vector can be described directly as Vm with phase angle theta. And that's it. These vectors are known as phasors. Okay. These are known as phasors, SORS. And again, it's simply to make the math less complex. Okay. And then inductors and capacitors are also expressed as complex quantities. Those are not vectors. I want to be clear. Those are not vectors. We are simply expressing them using complex numbers. Okay. So inductors have something known as impedance. Capacitors have something known as impedance, meaning they have a value, magnitude, and then they have an angle. Inductors have an angle of plus 90. Capacitors have an angle of minus 90. So when we apply KVL and KCL, let's say we have our vector for the source Vs, and then we have ZL plus ZC, meaning the inductor impedance and the capacitor impedance. And we are trying to describe the voltage across the inductor and the voltage across the capacitor. So let's say VL plus VC. That voltage will have an angle. Okay, so if you add up only the magnitudes, it will not work. You also have to take the phase angles into account. So this would be VL with theta L. And this would be VC with theta C. And so in lab 6, what you're doing is we are applying KVL and solving it graphically. That's what's happening, okay? So again, review the lecture videos and then review the pre-lab videos. That will go a long way towards helping you with lab 6. And then, of course, also just for the AC homework, all right? So we are out of time today. We'll end class here today and we'll pick up here again on Wednesday.